Has it started? Yes. Okay. So basically, there is an exact statement that the total energy of my system is a unique functional of the density of my system and external potential acting on my system. And I can find my density by minimizing this functional with respect to electronic density. Okay, so this is basically what we ended up with. Let me go back to this stuff. Okay, boom, 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 boom. No, 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 no. Okay. All right. So now, so this is all pretty good. But what can we do about all this? So we need to have a practical way of solving this problem somehow. Does it do the recording? No.
Yes, it is recording.
So, of course, you can't make any progress unless you find some way of approximating this functional. What is this functional? This functional should be related to my system without any relevance to the external potential, because it's universal. It will still be there if there was no external potential acting on my system at all, like electrons in vacuum. Yeah, it would be still the same. So what that potential would contain, we think, it would contain probably kinetic energy, which will still be a functional of the density, would contain, of course, a contribution due to interaction between electrons. It seems reasonable to assume that a dominant contribution to this interaction would come from this Coulomb interaction term here, in which we simply replace ρ operator with the ρ density. So there will probably be a term like this. These are all functions, not operators anymore. In fact, this contribution can also be written as an integral of electronic density, and here the potential due to electrons. We can also write it down like this. But this is not all, right? There must be some other contributions, which we have no idea what they look like. We actually don't know how this term looks like either. So we're pretty much facing a problem as to how to approximate or how to find a way to write the kinetic energy of the electrons as a functional of the density, and how to write the rest of this unknown functional. Yeah, so that's a pretty complicated problem, right? So I don't know how far should I go into the story? Basically, there are a few things you have to know. Maybe this would make it easier to understand. One thing, the very important thing, is so-called Gilliam model. What is this? If you consider crystal, it consists of positive nuclei and a sea of electrons around them, right? That is a pretty complicated problem to solve, because the nuclear potential is singular at the positions of nuclei. It goes to minus infinity for the electrons. It's finite between nuclei, so you have a really large change of the nuclear potential, this V and E, yeah, this potential I'm talking about. This is, yeah, this nuclear potential over the space of the crystal. Yeah, so it's a rather complicated problem to solve. However, in the Gilliam model, this nuclear charge is smeared out over the whole volume and made uniform. So in the Gilliam model, you actually have a positive background of electronic charge. And on top of this background, you have electronic charge. And because the nuclear charge is uniformly distributed, electrons are uniformly distributed as well. But with the density, the correct density, or the correct number of electrons, say, per volume. Yeah. So the density as a function of the position will be wrong, of course, because it's uniform. In real system, it is not uniform. You would have concentration of the density around nuclei most and a bit less between them, right? Because of the nuclear potential. But in this model, in the Gilliam model, you have some simplification. So in that case, the total energy of the system would be a function of this electronic density, which is a number. This Ne is a number because it's uniform. So Ne times the volume of your unit cell would give you total number of electrons per cell, which for each model is a fixed number. For example, in lithium metal, you will have 1, yeah, valence electrons. The interesting point is that it is possible to very high precision to determine the solution to this using this method. And this has been done because the model is so simple, the physical model is so simple that this has been done. And then by doing that, it was suggested what these other terms must be. Okay, that's one thing. So we have a model which is rather simple, but which accepts a approximate solution, but to a very high precision. And you can do this calculation for different values of this Ne. So you can build this energy as a function of these values of Ne in this Gilliam model. Okay. But there's the other thing you can do. You can then say, okay, well, I still have this problem. With that technique, I have the total energy. So the sum of these all terms, plus the interaction with the external potential, of course. Yeah. It would be nice somehow to deal with this one as well. Here, you have two approaches. One, when people try to write these terms as a functional of the density and this term as a functional of the density, and that term would contain some differentiation of the density as well, as this term may not. This term may be fully local, which depends on the density only, but this term may contain some differentiation of the density, because the kinetic energy is supposed to have it. Yeah? And another approach in which this functional is fixed. And then all the burden is shifted to this one. In which case, this one could be either local or semi-local or completely non-local. So it contains some differentiation as well. So let's consider this second approach, in which this functional is fixed to a very simple kind of form. And that form can be judged from the following simple consideration. We know that electronic density must be positively defined in space. We can write this electronic density via a set of orbitals, which depends each on a single orbital, as rho of r, sum of all states from 1 till n. N is the number of electrons, and here we write this psi of r squared. This form is positively defined by definition, but it also contains these orbitals. We know that in the Hartree-Fock case, when the wave function is written as a single slated determinant, then one can show, I didn't show you this, but if you have this determinant, slated determinant, remember this one, if you now calculate from this slated determinant the electronic density, why this integration? You're actually arriving at the same formula, when this psi I are just these orbitals, as in Hartree-Fock. This is pretty amazing, huh? So if we were at the Hartree-Fock level, and the same actually happens when electrons are completely non-interacting, independent of each other, then the electronic density would be a sum of the squares, and this is easy to understand. Electronic density gives a probability to find electrons in different places of space, and so does this psi. For a single electron, we simply sum up these probabilities. So if you had non-interacting electronic gas described by a single slated determinant, you would have, for the kinetic energy term, an expression like this. You simply sum up kinetic energies of each electronic state psi I, of each single electron. So if you neglect electronic correlation effects, something which goes beyond simple slated determinant picture, then that would be a pretty exact expression for the kinetic energy. So if we accept this electronic density as our working horse, and shift all the unknowns of the density to the unknowns of the wave functions, these many wave functions, we would then have a problem in which this T of rho would become a functional of these functions. We can also write the electron-electron term, it's called Hartree term, because rho is also functional of these functions. And what about these ones? These are all other terms which are to do with the fact that, in fact, our electrons are not described by a single slated determinant. There are many more in the CI expansion. These are all assigned to correlation effects. There's also exchange effects, which are present when we use a single slated determinant. And when it is not present, when instead of the slated determinant, we simply use a product of functions, so-called Hartree approximation. But on top of that, there is also some effects which are to do with the fact that one can excite electrons to in different ways to fill up different states, and therefore add up more than one slated determinant in this expansion. These are all called correlation effects. So all this in here, plus, we don't know what that is. If we replace the kinetic energy, but that very simple functional, we make an approximation. So that functional then should contain also a correction to this term as well. All in all, now you apply this theory to a known problem of a Gillian model, from which you can get this whole thing, and then from that, just by subtraction, you can get this term as a function of this NE. You see? So assuming Gillian model and adopting this very simple expression for the kinetic energy functional, we kind of put all the weight of unknowns on that object. And that object in the Gillian model would only depend on the electronic density in the Gillian model. And we know the whole thing. So that time minus this would give us that. And that we know is this. Plus the interaction with nuclei background. Yes? You see? So we have a way for that model to determine the rest of the functional, but not as a functional, but as a function of the electronic gas density in the Gillian model. And then what we do the following. We break up the space in the little volumes, and we assume that within each volume the density is constant, and therefore would be given by a number like this one. But it could be different in different regions of space, you see? And then we represent this energy, as a sum of all these cells in space. And there will be a term, how shall we call it? Exchange correlation term, which depends on the density in that particular cell. This is a number, not a function. And that term we can actually rewrite as an integral of this exchange correlation as a function of the density of space. I don't have enough space now. Where this dependence is the one we extract from this Monte Carlo simulation. This exact calculation which has been done. So you see, we assume that even though the electronic density changes in space for a real system, within each such little cell, we accept the dependence which comes from this Monte Carlo Gillian model calculation. Does it make sense? Hmm? Hello?
Yeah.
Felipe?
Oh, you mute yourself.
He mutes himself, but is he still alive there?
I think so.
I'm here. Can you hear me?
Yeah.
How did I mute myself? What? Okay. Sorry. In the Gillian model,
Because
are you
I'm really surprised you're silent.
I'm sorry.
So long, yes.
So in the Gillian model, are we considering all electrons or just the valence?
Yes. All electrons, all nuclei, but the nuclear charge is completely smeared out, uniform over the whole space.
Okay.
And therefore, the potential created by these nuclei would also be uniform.
Yes.
Just a constant.
Yeah.
Therefore, electrons would also be uniform. There will be no kind of like this. It will be completely uniform, constant over the whole space. Still, the integral of the density would give you the number of electrons.
Mm-hmm.
So if you integrate this density over a finite volume, like a unit cell of your crystal, you will get the number of electrons in that unit cell.
Okay.
Yeah, but it would be a number, and in that Monte Carlo calculation, now exist other calculations. For instance, let me show me the book. The book. Where's the book? I closed it.
I think so. Which one?
I might have closed it. Oh no, it was there. So there is that was taken from another book, but still. Where is it? No. Total energy of the electron gas in the Gillian model. You can write down the total energy of the electron gas in the Gillian model by a set of diagrams, and if you calculate each of those diagrams, you will get something like that.
Okay.
Friedberg, and Rs is the radius of a volume, spherical volume, occupied by a single electron. You can easily work out that this is related to the electronic density.
Okay.
Yeah, so you can actually get for the Gillian model an expression for electronic density.
Okay.
Yeah, and that would be a function of that density of the electrons. All right.
Okay.
See, there's some non-trivial like
yes, elaborate. Okay.
Yeah, and this comes from all these diagrams, and there are only 4 of these diagrams. In fact, there's 6 or 5, but one is the same. And there's pretty interesting stuff behind this, because some of the diagrams give an infinite contribution, but if you sum them all up,
they cancel each other.
You have a finite. For example, this diagram gives an infinite contribution, and the result of the reason for that is that this kind of interaction line and that interaction line correspond to the same momentum, q. But that diagram, which also appears there, has this q repeated 3 times. That one 4. So the interesting fact that people found a long time ago, I should say, that if you sum up all these diagrams to infinity, you actually have a renormalization, which means that a single wavy line is replaced by kind of a double wavy line, which renormalizes electron interaction, and that electron interaction is not any more singular at q equals 0. So you arrive by summing up an infinite number diagrams, each given an infinite contribution. You get a finite contribution.
Okay.
Yeah. And even though this sounds a bit weird, but this is what it is.
That's fine.
So, so either way, you have a way for this GLU model to perform a calculation. With Green's functions, with these diagrams, we can add more diagrams, more and more diagrams. Each diagram becoming more and more cumbersome to calculate. But these are all just multiple integrals of known functions. So you can calculate these integrals. There's no and more today on today's computer facilities, you can do up to whatever order you like. Yeah, so you can do the calculation very, very precisely, and from that you can extract this extra term, which we know little about, this one, for the GLU model to a high precision, and that term would depend only on the constant value of the density. And now we make a little kind of step aside from this GLU model and say, okay, this is the GLU model in which nuclei are smeared out. But let's consider nuclei now real, for real. They're not smeared out anymore. As a result, the electronic density is not constant anymore. Still, we can split up the space into small regions, small cells, and assume that within each cell, the electronic density is constant. And therefore, this contribution to the energy associated with this little region of space, we can borrow from the GLU model solution. And then we simply sum them up. And when we sum them up, of course, each cell would have a different value of this density. Okay, but still, the dependence will be the same as in the GLU model.
Yeah.
Of course, this is a picture of these cells. Nobody does cells. We then use a limit and make from the summation over spatial cells a spatial integral.
Okay.
And we arrive at something like that. And that dependence will now be a functional of the electronic density.
Okay.
Yeah. So now we have something like that. Let me just show you in the book. Oh, by the way, these are so this is called LDA.
LDA.
Local density approximation. What I just described. Here you can see these functions.
Yeah.
For the correlation effects, and there is also a function for exchange. These are all functions of RS, and RS is related to electronic density. So it's a exchange functional, which is this, and the correlation functional. So this is Perdieu-Zunger did this a long time ago. They used Monte Carlo, not Green function, but then calculation was repeated, I believe, with Green's functions. And this is how the density and RS are related, you see? Simple formula. And what I would like to show you is now, where is it? Okay, so there's so where is it? So basically, this is what I just explained to you. Yeah. The functional, universal functional, would correspond to the electron interaction functional, kinetic energy functional. Electron is not just this; it's more, because this is just a Coulomb interaction, but there are all sort of correlation effects, exchange effects, then we came up with the full functional will be this, because you have an interaction with the with external potential as well. So that quantity is the universal functional, yeah, of the density only. And then what we do, we replace the density with just the sum of psi squares. We introduce orbitals. and we write the density as a sum of their squares, then we arrive at a very simple, at a very simple expression for the kinetic energy, as for this independent electronic gas, one electron gas. And then we I'm trying to simplify the picture. Here we go.
Yes.
And then we write the total energy. We write the total energy as a functional of these orbitals.
Uh-huh.
And the functional depends on this functional of the kinetic energy, Hartree functional, this one, electron-electron interaction, interaction with the external field, and all the rest of it, which we don't know, we cram in here. Exchange correlation functional. So it includes correlation, exchange, and the kinetic energy error we're making by replacing the actual kinetic energy functional with this functional of the kinetic energy for the independent electron gas. So all the rest of it is in here. And we make an LDA approximation, as I explained. So you see it's here.
Mm-hmm.
Yeah? Electron-electron interaction, exact functional minus Hartree functional, this one. And exact kinetic energy minus this T naught.
Yeah.
So all is in here. So all the unknowns we collected in one term. And at that term, we borrowed from this Monte Carlo simulation.
Okay.
And replaced with this integral over space. This way, we created a functional, the final functional here, which is functional only of the density, but density is written via squares of orbitals, so it is functional of the orbitals.
Okay.
So now we arrived at some kind of functional. Let's write it. E total.
I don't know why, Lev, but could you minimize the PDF? Even though you change the programs, the PDF is on front. There you go. Thank you.
You mean not minimize, but yeah, it covers.
Yeah, it comes. Yeah, it stays in front.
Yeah. So this energy is a functional of all the orbitals, and in fact of their complex conjugate. But if you don't have magnetic field, if you don't have anything funny, wave functions can be always chosen real. Okay. So we just assume that. So we won't bother ourselves with this. So you have kinetic energy, this one, which is functional of the orbitals. Yes. Plus we have Hartree term, which is functional electronic density, and also eventually of the orbitals. Plus we have this term with external function, with external interaction potential, and this is also sum of the orbitals, and therefore it is a functional of the orbitals. Plus finally we have exchange correlation term, which is functional of the density, and because the density is written like this, it's also functional in the end of the orbitals as well. So we basically arrived at a picture in which the whole energy is a functional of these orbitals. But these orbitals we would like to be constrained by a condition that psi I module square integrated over space is equal to 1, in which case this rho, when integrated over space, would be equal to the sum of the ones up to n, so it will be equal to n.
Yes.
The total number of electrons. That's kind of reasonable to assume, yes?
Yes.
Anyway, these orbitals are introduced somewhat artificially. In exact theory, we need to deal with a single function, psi, rho of r. We introduced instead of it n, capital N functions, psi. Yes? And we made each of them normalized to unity. And interpreted this as wave functions of each electron, one particle, functions of each electron. So the whole electron density is made up of densities associated with which each electron separately. So it's a kind of independent electron approximation, if you like, but electrons are not fully independent because of that term and that term. So when we write equations for these orbitals, we will see that the potential in which electrons move is an effective potential, which is to be obtained self-consistently. Yeah, and that corresponds to the fact that there is a one-to-one correspondence between exact system in which electrons move as they please, with the all complexity of the Schrödinger equation, and one electron system when electrons are independent, but they move in a special effective potential acting between them. So there's a one-to-one correspondence between these two systems. Of course, we don't know what this effective potential is, but it exists.
Okay.
Yeah, so that's the main idea of this Kohn-Sham approach, that it is possible to find, no, not to find, there exists this effective potential in which each of those orbitals live. Yeah, so how can we do this? How can we find? What we need to do, we need to vary that functional with respect to the orbitals, subject to a condition that first of all the orbitals are normalized to 1, and also the orbitals are orthogonal. So basically I can write both conditions in that way. Yeah, this is a conical symbol, which is equal to 1 when I equal j, which will give you normalization, and is equal to 0 if I is not equal to j. So the orbitals will be orthogonal and normalized to 1 each. So at that point, I simply do a variational approach, apply a variational approach to this, and I set up Euler equations subject to this condition. So I use so-called Lagrangian multipliers. So this is all here. If you want to follow this, this will be at some point explained here. So we vary the total energy, this one. So it's an effective functional. So this is the total energy. And what is here? These are constraints which we put on the orbitals during the variational approach. So this is that envelope integral minus delta conical symbol. So this should be equal to 0. So this is a constraint, yeah? And these are Lagrange multipliers. There are many constraints because there are many of these orbitals. And we would like to ensure that when lambda and lambda prime are the same, it would be 1 here, and different, there would be 0 here, yeah? And what we need to do now is to vary that object with respect to these orbitals. So this is done in a few steps. You vary that with respect to the orbital, but varying with respect to the orbitals. What you need to do for some of the terms, which depend on the rho only, you need to first vary with respect to the rho, and then the rho with respect to the orbitals. It's a chain rule from differentiation. For some other terms, like kinetic energy, which depends on these orbitals explicitly, we should have it here. Yes, the varying of the psi lambda would simply give you this. Yeah. So when you do this now, when you apply this variational principle, you will get an equation like that. Yeah. So this comes from varying all this energy, and the second term, this one, comes from varying this bit, Lagrangian bit. Then what you can do next is to yes, and this operator G contains the Hartree potential, so it's a potential created by electrons with a density rho, external potential, and this bit is to do with this extra term, which we determined from the Monte Carlo, or determined from Monte Carlo by Perdue-Zunger. Yeah, which is a function of the density. So this doesn't seem to look like a Schrödinger equation, yes, because of that. But it's possible now to transform it into that way, that form, by simply making a linear transformation of these orbitals, such that in new orbitals, the electronic density is still a sum of their squares, like here. It's still possible to do it. And then one can show that sum would turn into a single term like this. So these phi lambda are now different orbitals, but still the rho is the sum of their squares. So this G is that effective potential now.
Okay.
So let's try to understand where we are now. According to the Hohenberg-Kohn theorem, there exists a functional of the electronic density, minimization of which would give us the exact electronic density, and therefore, by substituting this electronic density into that functional back, we will recover the exact value of the total energy.
Can you just minimize the PDF? Sorry, Lev. It's still on top.
I'm not writing anything. I'm not writing.
Oh, okay. Sorry. I thought you were.
So I was not writing. Yeah.
Okay.
So I'm just verbally saying.
Yeah. Okay.
This is Hohenberg-Kohn. So there is a functional, and we know it consists of two parts: interaction with the external field and the universal part, both functionals of the density only. And we know that if we vary that functional with respect to the density and obtain the minimum of it, that would correspond to the ground state of our system. Yes. So we will have the exact value of the density and the exact value of the energy. And because the external potential is a function of the nuclear positions, so this energy would correspond to particular nuclear positions. Yes. Now we change the nuclear positions and we perform the calculation again with the new potential from the nuclei. Again, the same functional we take, but just external potential will be different, right? Because the nuclei changed their positions. Yeah. And we minimize that functional again. We get a new energy, new density, and so on. We continue until we decide to drink coffee. Okay. And this way, we will be able to map up the total energy of the system as a function of nuclear positions, so the potential energy surface. But the problem is that we don't know that universal part of the functional. Yes. So here comes this Kohn-Sham idea. We write the density, which must be positively defined everywhere in space, as a sum of squares of some functions. That ensures that the density is positively defined. Mm-hmm. And also, as a byproduct, it introduces these functions, which can be interpreted as electronic orbitals. Yes. Then we do a little kind of manipulation, if you like, of that universal functional. We write this universal functional in a specific way. Mm-hmm. So we write it in such a way that we introduce the kinetic energy written explicitly via orbital. So the kinetic energy functional now is set up explicitly. Before we didn't know what it looked like. Mm-hmm. We write explicitly Hartree functional, which is interaction of electronic densities written via these orbitals. Yes. And this universal functional minus all this is what is left. Yes. Which is this. Yeah. And for that one, we take its kind of functional form from separate calculations made on the systems, which we can actually solve with quite good precision. Okay. And we do this calculation for different densities, and therefore that term we have as a function of the density. But of course, in real systems, the density is not uniform, so we make it an integral and assume that within each little cell, in each little space, dr, we can borrow this expression for the energy versus density,
Okay.
and then integrate over space. So that is basically what we do.
Okay.
And the only difference is in how we choose this term. In LDA, which as I just explained to you, that form is taken in a very specific way. So this is exchange like this. This comes from these calculations, Monte Carlo calculations, and correlation effects is taken for that. So this RS larger than 1 corresponds to low density and this high density.
Okay.
Limit, yes, because RS is the radius. So if the density is high, the radius is small. If the density is low, the radius is large. Yeah.
Okay. Yeah. So you just use it now.
So this is the idea of the LDA. So this is what it is. Yes. So LDA contribution to this expression for this exchange correlation potential is the formula which I wrote to you as well. And by varying this with respect to the density, this is what you need to do to determine this potential, exchange correlation potential. Remember how we obtained this G.
Yeah.
You obtain an explicit expression, which is here in LDA. So this is what it is. And that expression is known. So this XC is actually a function, not the functional anymore. It's a function of rho, with rho considering as a number.
Okay, for rho. Okay, for rho. Okay.
Yeah. So, yeah.
Okay.
So this differentiation. So if you take this, RS is related to rho like this, so you can easily differentiate that.
Okay.
But nowadays we have many more various approximations to this exchange correlation.
Okay.
So this was LDA, local density approximation, but there are more of it. So there were extensions called generalized gradient approximation. In these approximations, LDA is local because LDA only depends on the density. Remember this? Oh, I'll show it again. It depends only on the density via RS. It's just a function of the density.
Yes.
But in GGA, you have also gradients of the density included as well.
Okay.
Because there's no limit to what you, there's no constraints on what the form of the function is. Who knows what that is, right?
It could be infinitely differentiable, so it could be anything.
Yes, it could be anything you like. It could be, we don't know. We will probably know. But so in order to improve on this LDA, which splits up space into little volumes, within each volume you take this constant density, you actually allow for the density, for the functional to depend on how the density changes across space, and this is described by the gradients of the density. Yes. So of course here in the book I don't have these explicit expressions, but if you're really interested, you can find these explicit expressions in papers and other books, and there are many other things people do. There are many such functionals. So we call them flavors. There are many flavors of the density functional existing. There are GGAs, maybe 20 different ones.
Oh, okay.
But then people, maybe more. But then people included also so-called van der Waals effects, which are not covered by this LDA and density functional. We know that from calculations. So there was an activity some time ago to actually go beyond DFT, but still keep it to the constant picture. In other words, find an additional correction to this universal functional, which comes from the Monte Carlo Gilliam model, which cannot actually describe the van der Waals interaction by definition because of the module. That's why in LDA the van der Waals is completely neglected, because it's based on the Gilliam model, in which density is uniform, and therefore van der Waals effects are not included at all.
But if you make your grid small enough.
No. It's still van der Waals is not accounted for.
Okay.
It's still not accounted for. Because van der Waals is related to the dynamical effects as well, so how the density changes, and the LDA doesn't cover that. These were all static calculations. No, what I said is probably not quite correct. These are quantum dynamical effects, so these are included, but if they are included in some form or way, it's probably insufficient.
Okay.
So what people try to do is to come up with some additional contributions to this universal functional, which would account for the van der Waals interaction. And Landreth contributed he was the first with his group who invented such a functional. So it's you can consider this as just another DFT type functional.
Okay.
Which is a bit more complex than DFT functionals people use, but still there are schemes existing which account for it with a very little additional effort. Yes.
Okay.
There's also a way to account for the van der Waals by simply adding to the total energy of the system some analytical function of nuclei positions. This is what we call Grimme-like functionals. This is very cheap because you perform a DFT calculation, you calculate your forces, and you simply add to the energy some value corresponding to this additional function of nuclear positions, and to forces an additional contribution due to differentiation of that additional contribution. And you minimize your energy. So the actual solver of the electronic structure, in other words, the Concham equations themselves, they remain the same. So you use the same solver as before, but when you calculate, so this is what you solve, yes, but the expression for the forces gets an additional contribution, and expression for the total energy gets an additional contribution. So that affects atomic geometry, relaxation procedure, and the final geometry, and the final expression, a final value of the total energy. But because the additional numerics involved is so incomparable with the numerics associated with solving this equation, and that equation has to be solved self-consistently because this potential depends on the rho, and the rho is constructed as sum of the phi squares, yes? Remember, we discussed this at the very, very beginning last time. Let me find this. It's here.
Yeah.
You start from a position, then you do electronic iteration.
Electronic steps, yeah.
Then you move to a new position, you do a little bit smaller number of iterations because you're starting from the better initial guess.
Yes.
Then you move to a new position, and so then you converge. So by this, I mean basically a way to solve this equation self-consistently. So the way to solve it self-consistently is that you start from one rho. With that rho, you calculate this functional. Then with this functional, you solve the quantum equations, and you get orbitals. And you get not just one orbital, you get not just n orbitals, you get actually more orbitals. So some will be occupied, some will be unoccupied. Yeah, and the density is a sum of all occupied orbitals from 1 till n. Occupied, the lowest, you take the lowest because you have many, and you populate them with electrons up to n electrons. Yeah.
Yeah.
So these are all occupied states. So this will be psi I r squared, and there's the same r here. Yeah.
Yep.
Once you get this orbitals, you construct this density again, and from the density you again calculate your g, you update your g, you update your orbitals, and you run this until you.
Okay, so that's the electronic calculation.
This is electronic calculation. Nuclear
the ionic steps.
Nuclear positions fixed. Yeah.
You calculate the density, you calculate the green functional, you calculate the Key-S equations, you get a new orbital. The orbital you find, okay.
Yeah. So at the end of this position, when you believe it converged, so let me do it that way. Or maybe that's not very good. Yeah, that's not how it goes. Yes, here converged, and no here. Yeah.
Yes.
So when it converged, what do you have? You have the electronic density. You have the total energy, which is functional of the density, and you also have atomic forces.
Yes, from the Feynman-Hellman.
Yeah, you have atomic forces acting on atoms. So this is a pretty expensive step, but it all depends on what is the actual density you started from. And of course, when you start a new system, you have no idea what the density must be. And so you start, if you take different codes like VASP, you will find that there are different flags you can specify in the input, which would initiate a different procedure for choosing the initial density.
Okay.
A sum of atomic densities. So they have atomic calculations done for all atoms of your system. And they simply take this rho of R as a sum of these atomic densities. That in many cases is a pretty good result, but you can take it uniform, or you can take it from some external file. For instance, that external file could be from a different calculation.
Okay.
Yeah. For example, another geometry of the same system you performed before. Of course, in that sense, you might be biased, because this is an optimization procedure. So basically what you're doing, you're minimizing the total energy with respect to the density, right?
Yes.
So you may arrive at a spurious solution for the density, not the exact minimum. Hohenberg-Kohn theorem states that it must be a global minimum of the functional with respect to the electronic density. There is no way you can prove that self-consistent procedure starting from some density would converge. It will converge, but will it converge to the right one or not? We don't know.
Okay.
So we can only try doing this from a different initial density and see whether it would converge to the same or not.
Okay.
We also can have a look at the electronic density and the energy and see whether these are reasonable or not. Yeah. from the physical point of view. So it's experience and results of the calculations. If you have results which are reasonable, and you may explain the results of the experiment in some way or another, then you would say probably it's okay. But if you arrive at something strange, or you do not have confirmed results of the experiment, it could be, of course, that your model is wrong, but it could be that simply DFT procedure converged to something unreasonable. Yeah, something different, unreasonable. Yeah, so we don't know. We don't know. But it's good to have this in mind, as this is important to have in mind. Yeah.
Yeah.
Okay.
So this, in terms of VASP, this is our outcar.
This is what?
The outcar.
The outcar. Okay. In terms of VASP, maybe.
Right.
Shall we? So. Okay. So let me say a few words about VASP. So that will be number 2. Oh. Few words about VASP. Of course, VASP changes. And I now notice I haven't run VASP myself for some time now, I should confess. And I looked some time ago. They made some changes, but basically, the idea hasn't changed. So VASP has a set of input files and output files.
Yes.
Input. Oh, what is that doing? Input. Output. Okay, input. Postcard. This is the geometry file.
Yes.
You specify where nuclei are, and also because the code is based on periodic boundary conditions, probably we need to go through this as well with you. Unit cell, these kind of things, because these are important.
Good. Yes.
Yes, I think we need to do this actually. Yeah. So this is postcard file. Then you have K-points file. And again, I need to explain this. Did I explain that before? Probably
K-points. No, I don't think
so. No, plane waves.
Oh.
Ever done something on plane waves?
I don't think we did.
I don't think so.
Or did we?
Oh, no, we didn't. Aha. So this would be something for the next time, I think. A bit of more practical things. No, there's nothing on plane waves. Aha. So, okay, yes. So we need to do this. K points. Then in-car. In-car is a logical file. So these are K points. Geometry. Logic.
Then the postcard.
So the in-car file, you explain the logic of the calculation. So what do you want to do? What are the parameters? So for example, how would you choose the initial density for the self-consistent procedure? How many steps for the ionic relaxation? How many steps for the electronic relaxation, the self-consistent procedure? Blah, blah, blah. What functional to choose? Many things. In-car, and finally pod-car. Pseudo-potential. So that's something we need to consider. Let's just make a list. Pseudo potential, plane waves, K points, lattice. Yes. Anything else?
Lattice. I guess we're going to talk about a little bit of
We'll talk
Brilliant Zone
about
as
direct
well.
lattice, reciprocal. So say again?
Yeah, we're going to talk about reciprocal space and all that.
Yeah. Reciprocal lattice, all this. Plane waves, K point, sample, E cut, all these things.
Oh yeah, he cut.
Is there anything else?
Well, this.
You know what? If there is something else, we probably will remember.
Yeah.
So pseudo potentials, roughly speaking, is a way to discard co-electrons from atoms.
Mm-hmm.
But you have to do it properly. You can't just discard them. You have to
Okay.
really replace them with something else.
Okay.
Yeah. So this is what the pseudo potential does. So in the end, you run only valence only calculation.
Okay.
Yeah. What do you have in the output file? You have an output file, outcar file. It's a main output, which contains iterations, energies, forces, quantum energies. These are energies, total energies.
Yeah.
Due to relaxation, for example. Forces, quantum energies are there. There's a lot of stuff it contains.
Yeah.
So basically, this is the main file. You look at that file and you see whether the calculation finished. So this is all inside here. There. You also have many other files. So there's a DOSCAR.
Oh yeah,
There's a wavecar. Concar. Charge car. Is it like this? Charge car, maybe. Or many other. Oh, the pot car. So no, pot car is here. What's called P. So, there are many files. So, so these are wave functions. So this file contains actually in some form this psi I of R orbitals. This file, new geometry. This file contains rho of R. This file contains these eigenvalues of the Conchem problem. Yeah, these energies.
Okay.
These energies. Epsilon
Uh-huh.
lambda. Yeah. But there are many other files which WASP creates, which is a pain. I even have a script which removes all the files because it's so annoying. You have like 20 files or something created by WASP. If you run WASP, you know.
Yeah, I remember.
Okay, I think this would be enough for today. What do you think? We but do you think you have some better idea now what this is all about?
Yes, and more than that, I know what to look for as well.
You say again?
I know what to look for as well now.
I look for, huh?
Yeah, oh, I need to understand this. Like, what is this again? And then, okay, oh, I need to read about this again. So
yes. So there are many things you can think of. Yes. Of course, when you start for the first time, any calculations, Jing, did you try to use WASP at least once?
Yes. Yeah. Well, so the only thing that I've done is WASP.
You done, or Jing?
Oh.
No, I haven't done that.
You haven't done, but you will have to do some, yes?
Yes.
This is your project, so we'll have to somehow. So, the route to using WASP is a little bit long, but we can try to set up with you a set of calculations. But we need to talk about boundary conditions. We need to talk about the lattice, plane waves, sphere of the potential. We need to talk a little bit about all this stuff. And then we will try to set up simple calculations with VASP. That would be, say, calculations for a perfect crystal. Say, how to find the lattice constant, how to look at electronic density, how to preview the density of states. So we have to talk about density of states, by the way. This density of states. Check the density of states. Rho of R. So these are all practical points. Yeah. So once we know a little bit of this, we can try to look at surfaces. Yes, it will be surface. Molecules. So these are all practical kind of things. Then we put a molecule on the surface. So I'll try to guide you through this, yeah. And of course, we will have to maybe at least, I will probably, I don't know, would it be useful to have a session on Tether?
I think it'd be good, yes. Again, I know a little bit of Tether. I know how to create a surface, I know how to read and all that. But there's a lot of stuff that I haven't used. And for Ying, it will be very, very helpful.
Okay. Then there is also a thing about STM and AFM. What about this?
Yeah, it would be good to talk about that as well.
Right. So we can, but we don't need to talk about this straight away. Yes, we can mark this here as possible objects of discussion. But okay. So I suppose we are done for now. And I'm kind of happy that we finished at least we kind of finished a self-contained session. Yes. Self-contained. So these sessions are self-contained. So there's nothing kind of left undiscussed. Okay. So these all other things are new things. Yeah, but I'm afraid we'll have to do it after New Year.
That's fine.
Sometime in January, right?
That's fine. Whatever it's good for you, love.
Yeah. Because it might be quite hectic this time, and I would like to have some rest as well. But you have a lot of things to do yourselves, so yes. I suggest you try to read something around these topics we just discussed. Yeah. Okay.
Can I ask you an enormous favor? I have your book, but would it be okay if you send me the PDF as well?
Yes, I can send you the PDF. Do you want the PDF of these lecture notes?
Yes.
But just not for distribution. These lecture notes and the PDF of the book. Yeah.
Yeah, of course. Yeah. No. It will be. In a vault.
Yeah. So, do you want? I would like to put some bit more stuff into the lecture notes. I'll send you not today.
Okay.
I'll send you in a few days. Is it okay?
That's fine.
Yeah.
Some other thing, just of practical purpose. Right now, we're trying to create a project at the Nottingham cluster. Well, basically, I already created a project. Now I need to actually have access to it.
Wait a second. Just there's a problem. It's 70 megabytes. So okay, I will have to create a link.
Okay, yeah, it's fine.
I will have to create a link. Yeah. Okay. So again, project. You said some project.
Yeah. So I'll try to basically be able to run the calculations on the Nottingham HEC. It's a bit slower than in King's College. In King's College, we got this done in a day. In Nottingham, it's been a week now.
What do you mean King's College? You mean not King's College? You mean the cluster?
The cluster. Well, yes, the young previous Thomas.
Young. It is not King's College.
Yeah, I know it's UCL. Yeah, but
yes.
It was done by someone by King's College. That's what I mean. Someone at King's College said, "Okay, let me create an account for this guy."
Yes.
At Nottingham, it's taking longer.
Yeah, of course. But do you still have an account? So
yes, I do. I just tried before this. I tried to SSH to my account, and it's still there. The files are still there, and all that.
So just one sec. I just sent you the book, the many body book, but it's not complete yet.
Yeah.
I'm putting in stuff in, not complete. It won't be complete for a couple of years, but I'll send you the current version. You can start reading it if you like.
Yes.
But I will be working on this over this coming few days, and I will put a bit more stuff, and I will send it to you. And after that, I won't be doing anything for a year or something.
Okay.
So yeah, and the book, the solid state book, it's 70 megabytes. So what I will do, I will create a link and I will send it to you. Okay. And you would share it with Jing, yes?
Okay. Yes, I'll share with her.
Okay. So now continue with your Young account.
Yeah. So I have a Young account. I can SSH through it. Yes. The binaries of VASP are there. I haven't run anything on Young yet, because if I run something, then that comes out from your budget.
No, that's okay. Our budget is kind of infinite or something.
Okay, then I'm gonna try to run something very simple, just to make sure that.
Yeah. We will run everything on there.
Okay.
If that's okay. So we will try to set up maybe next time. We will try to set up. We will try to set up a few kind of simple calculations. Even now you can try to set up something really simple, like a lattice constant of kappa or lattice constant of something, but I don't know. Do you think you would be able to do this? Or
yeah, I think so. So I've done gallium arsenide. Yeah. Well, I don't know if you're.
Okay. What you can do?
So I know how to create a crystal. I know how to create a surface. And then I know how to create some vacuum, so we can put the potentials. Then. Yeah, I know a few things, not a lot.
So, Jing, you can do it together. What you need to do? So let me explain to you simple things you need to try. That would sound a little weird because we haven't covered these other things. But if I treat you like monkeys.
Yes, please.
Then this is what you need to do. So take kappa. Gallium arsenide is a little bit more difficult. Take kappa. Kappa is I think is the FCC cubic lattice.
Yeah.
With a single parameter describing the lattice geometry.
Okay.
Let's call it A.
I'm gonna call it. We're gonna do with silver if that's okay, because it's gonna be useful for us.
Silver is the same. Silver is the same.
Okay.
Then what you need to do is to set up VASP calculation with some density function. For example, take GGA per Dewang or PBE GGA, and specify the correct pseudo potentials, which will be silver.
Okay.
And there could be some choice of different pseudo potentials, but we have to go. We can't do it now. But just choose a pseudo potential from. If you have one pod car, that's fine.
Yeah.
And then choose the primitive unit cell.
Yep.
for the calculation, that primitive unit cell should contain just one single electron for silver. Is it correct?
I don't know what the silver distribution is for silver.
If you no, I have to look up. I have to look at no silver probably won't be just one electron, but if you take something like sodium or potassium metal or lithium, that would be just one single valence electron. For silver it will be more. You have to look at the periodic table. But what you can do now, if you choose a primitive unit cell won't be a cubic, won't be a cube. And see, primitive unit cell is like a thing will be kind of skewed parallelepiped. Yeah. And then you can choose a K point something like 3 by 3 by 3 or 2 by 2 by 2, and run a simulation with the fixed geometry. And the particular value of the lattice constant. For example, take it from the experiment. You will get the energy. Yes? Then change the K point sampling to something bigger than 2 by 2 by 2, like say 3 by 3 by 3, then 4 by 4 by 4, 5 by, and run the calculation again every time. You will see that the energy of the system should go down as you choose more and more K points. But that dependence will not be very, very kind of straightforward, say. The other thing you can do, you can choose the K point sampling. We will learn next time that if you choose a higher cutoff energy, you will include more and more basic functions, plane waves, into the calculation, which would also guarantee the total energy to go down. So you can take the cutoff energy higher and higher, and for the given K point sampling, for the given set of other parameters, that only cutoff energy changes. You also see the energy would go slowly down. Then you choose the cutoff energy and K point sampling such that once you increase each of them, the energy doesn't change appreciably anymore. And you use these parameters, and this would be, for the cutoff energy, this would actually be default parameters in WASP. So the potential file already has a default cutoff energy, and if you have different species, it would take the largest cutoff energy out of all these species for the whole calculation. Because we will learn when we study pseudo potentials, this is actually the case. The atomic kind of configuration dictates what cutoff energy you should take. Because with the pseudo potential, you smoothen out the wave function inside the core region, and that depends on the core radius. So take this cutoff energy and K point sampling and changing the largest parameter. You should find that the total energy would form a kind of parabola around minimum value. So then you can extrapolate this parabola, these values into a parabola, or interpolate by parabola, and then extrapolate the position of the minimum of it. Calculate the energy for that minimum position of a parabola, maybe do a few more iterations. This way you can find the equilibrium lattice constant. That's the first calculation, kind of calculation you can do. If you take something like gallium arsenide, is it cubic? I can't remember now.
It is. It is the same as silicon. So it's.
So it's
silicon, but
it's cubic. But you have on top of the lattice parameter, you have also positions of these two atoms inside. Yes? So, but for each value of the lattice cell size, you would have the positions of atoms relaxed. If you specify relaxation. So you can do something similar to this. Then, so this would be a crystal. Then you will have to create a surface. A way to create a surface is actually described. There's a tutorial on the Tether website. which describes how to choose with tether a surface.
Yes.
Basically, the idea is that if you have three largest vectors of the bulk, A1, A2, A3, you have to choose a different combination of them such that there will be two lattice vectors, new lattice vectors, within the surface.
Mm-hmm.
And the third will be out of the surface. And tether can do this with some little steps, number of steps. And then you would build up your surface as two lattice vectors within the surface and one here out of the surface. And you can choose as many of an extension of this to specify a certain number of layers in your surface slab, because the surface will be described as a slab.
Mm-hmm.
Finite number of layers, which will then be periodically repeated in space with some gap between them.
Yep.
So what you can do then, you can create different surfaces of this type, then fix atoms at the bottom layers and start to relaxing atoms of the upper layers, and try this with different numbers of fixed layers versus relaxed layers.
Mm-hmm.
And by taking the energy of that system from the energy of the same system, from the energy of the bulk cell times the number of bulk cells in the surface,
Mm-hmm.
you would see as the number of layers is increasing, that difference goes to a certain constant value, which is called surface energy.
Mm-hmm.
It is to do with the fact that as the number of layers increasing, the layers inside the slab looks like bulk-like.
Mm-hmm.
And if you say have 10 unit cells, bulk cells along the surface, say 6 up to 8 cells inside that surface unit cell, which will be like a sausage.
Yeah.
Like bulk-like, but the top one here and top one at the bottom would not be bulk-like because they have no bulk cells above them or below them. So their energy will be different. So if you subtract from the energy of your surface cell, which consists of, say, 10 bulk cells, 10 bulk cells, and the energy of the bulk you have obtained before in doing the bulk calculation when you relaxed the lattice constant, you will have this this converge to a number as you increase the number of layers. You divide it by 2 if, say, both sides were allowed to relax, so no constraints at all, or you do something different when you have at the bottom fixed and at the top. So you have 2 ways of doing it.
Okay.
But you can extract the surface energy from this.
Okay.
Yeah.
Interesting. Okay.
So you can say by how much the surface loses. The system loses by creating a surface.
Okay.
How much of the energy. So this is something you can do. Then you can extend the surface. You can build a surface bigger than just the size of the primitive cell.
Yeah.
Then you can use take a molecule, any molecule, relax the molecule with lattice vectors to prevent the molecules to interact with each other.
Mm-hmm.
Then you can put the molecule on top of the surface and relax it on surface.
Yes.
And then you can do some other things.
Okay. So for I'll try not to keep you longer left. But just so for one thing that Phil said it would be interesting to do, that I already started thinking, to simulate C60, water on C60, and then put those few molecules on silver and look at the density of states.
What is that, the molecule? Water in C60.
Yeah, C60, water on C60, put the 2 on silver, and then look at density of states. So that's why I said, well, maybe let's do a silver then. But we
should be able to do this, but maybe we need to use not VASP but CP2K for that.
Okay.
VASP will be expensive.
Okay.
Well, we can use still VASP as a reference.
Okay. Let me ask you something. How do I, like most of the stuff you said, I think it's okay. I need to review the tutorial on how to create a surface, but I think I remember. But how do I get the potential files?
Pseudo potential files.
Yeah. So yeah.
Okay, so there is a way to do it.
Mm-hmm.
So if you have a license,
We do.
there's a site you should go to
Mm-hmm.
and download a file which contains all the potentials of all the elements.
Oh, okay.
You have to extract the archive.
Mm-hmm.
That you will have a set of directories with all the elements. I can show you how it looks like.
Okay.
It looks like something like that.
Okay.
Wait, I'll show you.
No, we definitely have the license.
You probably have all this, but let me show you. I should also have this.
The problem is I don't know what the website is.
Yeah. I think. Well, okay. Let me first show you how this looks like, and then we'll try to think of this website. Where should I go? I should go to software. I think. Bumps. Software. Where's software? Huh? What? Software. Then we go to WASP. You see my screen, yeah?
Yeah, I see.
WASP, and then WASP 5.2. And then you have these files. This this is the manual, but it's rather old. It's already 10 years old. Oh no, this is my license. No.
This is your license, yes.
This is my license. But these are okay. I probably don't keep it. But these are GGA.
For every single element.
Yeah. This is PBE. So this one GGA is probably that's one. I can't remember now. But these are different types of because there are different types of pseudo potential existing, and then there's this so you see this kind of file.
Yeah.
This is how you get it. And if you go to say PBE GGA and you look at this and each element says silicon, you have different types, which you have a podcar here.
Yeah.
So you want to open this podcar, it looks like this.
Yeah.
This is a podcar file.
Yep.
Which contains various information. So first of all, it contains here the number of valence electrons, the core charge, 12.
Mm-hmm.
Will be 12 electrons with this potential. And this is silicon, so it's probably a very soft silicon because the number of electrons is quite large. If we go to the browser and go to Mendeleev table, what?
How do you pronounce his name? Dmitry?
Mendeleev.
Yeah, it's hard for me. Mendeleev.
Mendeleev, something like that. Yes. Oh, open the. Okay, silicon. Silicon is here.
Yes.
So it contains silicon. So its valence shell is only 4 electrons.
Yes.
But before we have 8.
Yes, the neon.
Before 12. So that pseudo potential only takes one S shell as 4. So the 2s2p shell will be treated as including electrons. So it's almost all electron calculation.
Okay, so he's including a lot of electrons.
Then you have ultra soft pseudo potential. It's false, so it's not ultra soft. It's a PAW. It's a PAW pseudo potential. So it's a pretty good, but it's very expensive because you have too many electrons, and also you have to specify a very cut of energy will be what is the cut of energy?
A cut.
I think here. I can't remember where it is.
So it's uncut. Yeah, so it's the Nmax.
Emax.
Nmax on the podcast file.
So
yeah.
this is that number.
That's the Ncut, yes.
This number is very high, 475. This is for that pseudo potential. What about, what is that? Just normal silicon. There is no normal silicon? Ah, there is a normal silicon. Here's a normal silicon. Let's open this one. This is normal silicon. Aha, it has just 4 electrons. So it's only the valence shell is included. And you see Emax 245, almost 2 times, more than 2 times, no, almost 2 times smaller.
Yeah.
Okay, so this will all come clear when we explain this, when I explain to you what the pseudo potentials are. So there are different types of pseudo potentials files you can take depending on what you're doing.
Okay.
Yeah. Okay. Now, how can we get the pseudo potential file? If we go to VAS, you need to go to VAS portal.
Ah, okay.
But and once you log in, actually, no, do I have, does it remember? Ah, it does.
Look at that.
That version not licensed. I don't have license version 6. But I do license session 5. Okay, license. Okay, they know everything about me. Potentials.
Oh, and then you just download there.
Yeah.
Okay. I'll check. I know I have, and I'll check. He probably doesn't have a username. I don't know. I'll probably have to create an account, but that's fine.
So you have to create an account. Once you have the license, it will ask you. So try to find. I forgot how to do it. It was a long time ago. Yeah. So that's what you need to do.
Okay, I'll do it now.
Okay, guys. I think
it's time to go.
Time to stop. I think. Yes.
Yes. Yes. Thank you very much, Lev.
Thank you.
So you're welcome.